Good morning. My name is Tayyab Adnan. I am a graduate student at Clarkson University. And today my presentation is on the measurement and characterization of chloride transport properties for Belitic calcium sulfoaluminate cement concrete. So Belitic calcium sulfoaluminate cement is an eco-friendly cement. It has rapid strength gaining properties which are due to the extensive formation of ettringite as the early age hydration product. The image on the right shows the formation of extensive formation of ettringite crystals after just 4 hours of hydration. So this rapid strength gaining property is one of the reasons why BCSA has been used as a repair material in US. But in the recent years, the benefits of BCSA being eco-friendly, having rapid strength gaining properties, has made researchers investigate its use in structural concrete. But we still need to have detailed knowledge on the strength and durability of this concrete. So more research is needed in that area. And my research is specifically related to a durability property, which is chloride-induced corrosion. There are two issues we need to address in this category. First, there is limited literature available on the chloride corrosion and chloride studies of BCSA cement. And second, there is contradiction among the results. Some researchers say that BCSA has poor corrosion performance, whereas field investigation has shown no signs of corrosion even after 23 years of service life and despite being exposed to de-icing salts. So, the objectives of my presentation, of my research, is to first evaluate chloride penetrability and corrosion test for application to BCSA concrete. The second is to quantify the chloride penetrability of BCSA concrete. The third is to quantify the corrosion performance of BCSA concrete. And finally, to identify the factors contributing to the observed performance. So for this study, I've used a range of water cement ratios for BCSA cement and cement concrete, which gives me a 28-day strength ranging from 40 MPa to 70 MPa. And I also have a control mix with Portland cement, which has a target strength of 28-day strength of 45 MPa. And for this study, I've used a range of test methods. So for the qualitative test, I've used RCPT, surface and bulk resistivity. And for the quantitative test methods, I've used the migration test, bulk diffusion and bonding test. And finally, for the corrosion assessment, I've used the test methods to to measure the corrosion potential and the macro cell current. Let's start with the results of the qualitative test methods. So for the RCPT, the test method gives you the amount of charge passed through the specimen in coulombs, and it also has a classification based on the charge passed, which shows the extent of chloride penetration. So here you can see that for BCSA specimens, overall the performance shows it has very low chloride penetrability. Now let's move on to the results of the surface resistivity, where again you have a classification for concrete for the amount of chloride penetration based on the resistivity of the concrete. Here you can again see that for BCSA, it seems to have fallen in the range of low to very low chloride penetration. So as far as we compare the results of RCPT and surface resistivity, they seem to be in agreement for BCSA concrete specimens. But when we look into the results of the bulk resistivity, you see a contradiction. Here the resistivity has dropped and it seems to fall in the category of moderate chloride penetration. What could be the reason for this change in BCSA specifically? One possibility could be the specimen conditioning. Because if we go with the standards, it suggests that we need to immerse the specimens in a simulated pore solution, which contains calcium hydroxide, sodium and potassium hydroxide. And I've taken a statement from the code that this is done specifically to account for the alkalis that were lost in the curing process, even if you use lime saturated curing. So when we look into the oxide composition of BCSA and Portland cement, you can see specifically that the BCSA has low alkalis compared to Portland cement. One possibility is, are we introducing more alkalis into the pore solution in that aspect and making it conductive, which is impacting the overall resistivity of the concrete itself? That's something we need to further study and investigate. Now let's move on to the results of the quantitative test methods. The first one is the migration test, which gives you the value of migration coefficient. A low value of migration coefficient is good in terms of having low chloride penetrability. So you can see that BCSA specimens seem to have a reduced migration coefficient as the water cement ratio reduces. So that's good. But when we look into the results of the bulk diffusion and ponding test, we see a sharp contradiction. Here you can see that the values are significantly higher, and specifically if we look into the result of 0.4 water cement ratio for BCSA, so B.4 is BCSA with 0.4 water cement ratio, you can see that for one case bulk diffusion, it is having very low diffusion coefficient, but when we have the ponding test, it is totally opposite, it's very high. So one thing we need to look into specifically is that the duration of the test method. The migration test is done for the test period is 1 to 3 days, but for the bulk diffusion test it's almost 60 days in my case. Okay, minimum should be at least 56 days. And for the ponding test you have a duration of 90 days. One thing with BCSA cement is that it's hydrated, it hydrates at later ages as well. So you have a cement that is hydrating, and that seems to have an influence on the diffusion coefficient. Now, I've just shared one of the plots for the diffusion coefficient. I've used MATLAB to calculate the values of diffusion coefficient and surface chloride concentration. And you can see that this plot with total chloride concentration and depth, how the pattern looks. So for the first top surface it is very high, and then it drops down and it's almost constant across the entire depth almost. So with this thing I would like to raise a very important question, which is, are the test methods developed for Portland cement concrete applicable to alternative cements? With this thought, now let's move on to the results of the corrosion assessment, where I've used G109 specimens and to study both the corrosion potential and the integrated macrocell current. And for this study, I've used two batches. The first batch consists of BCSA with different water cement ratio, but same curing period. And for the second batch, I've used just one water cement ratio of BCSA and then modified the curing period. Let's start with the results of batch 1. For the macrocell current, you can see that the integrated macrocell current is comparatively much higher for BCSA, and if we compare it with the cycles of exposure, it is crossing the limit specified by ASTM at just one cycle of exposure, and it keeps increasing. Now when we look into the corrosion potential based on ASTM C876, you can again see that BCSA specimens have very low corrosion potential, very negative, and based on the classification, this falls in the category of high probability of corrosion, which means 90% probability of corrosion, and low probability means 90% probability of no corrosion. So now let's once this exposure was the values were very high with just one cycle of exposure, I took out one of the specimen from the lot and autopsied it to see how the rebar looks. So the steel rebar looks like this. For all BCSA specimens with just one cycle of exposure, it seems to have a lot of corrosion going on of the rebar. Just a difference is that as the water cement ratio reduces, it seems to have a slight impact on the corrosion of the rebar itself. But if you see the Portland cement, which was exposed for 7 cycles of exposure, it still has no corrosion there going on. So now let's move on to the batch 2 results, where I've changed the curing period. And you can see that the macrocell current, the blue line, indicates the value for 28 days. And as I increase the curing period, you can see these values fall within the limit, up to 5 cycles of exposure. That is the duration that I tested the specimens for batch 2. And also for corrosion potential, you can see that 28 and 56 days fall in the category of high probability, whereas with 90 and 180 days of curing, it now changes to a region for uncertainty and finally to low probability of corrosion, 90% probability of no corrosion. So after 5 cycles of exposure, I autopsied all the specimens, and this is how it looks. So the first one was with just 28 days of curing and just 1 cycle of chloride exposure. And for the other ones, it is with 5 cycles of exposure and 56 days and 90 days of curing. You can see that there is significant improvement in the corrosion performance. There is comparatively much lower corrosion here. Now, I would like to share a simulation that tells you the possible hydration of BCSA cement. And BCSA, as I mentioned earlier, has a late range hydration as well, because it also contains Belitic and it hydrates to form majority of it forms Stratling-ite and some amount of CSH. And based on the results that we have observed, these products seem to have significant late range microstructure refinement for BCSA cement, and also they have an impact in increasing the late range pH, which is extremely important for steel passivation. Finally, I would like to conclude that the electrical tests have to show low chloride penetrability. However, specimen conditioning may cause erroneous results, as we observed for the bulk resistivity test. The second is that the migration and the diffusion tests show contradictory results for chloride penetrability of BCSA cement. The third is that the corrosion performance of BCSA cement improves with curing age. And finally, my future work will be related to further study the time dependence of chloride penetrability and the time dependence of steel passivation, and finally to work on a corrosion service life model for BCSA cement. First, I would like to thank Professor Robert Thomas for all his guidance in this research. I would also like to thank CTS Cement for sponsoring the research, and the Center for Advanced Material Processing at Clarkson University for its assistance in the research. And finally, I would like to thank ACI for giving me this opportunity to showcase my research. Thank you.